In this video, I'm going to be introducing you to the first big topic of Calculus 1, the derivative, one of the foundations of calculus. So, in order to explain what a derivative is, I first need to describe slope. So how do you calculate slope, right? So you calculate slope by putting the change in y over the change in x, also equal to y2 minus y1 over x2 minus x1. And these subscripts represent different coordinates. So you have a single point on your graph, x1, and you have another value of that point, the y value of that point, y1. You also have another point, x2 and y2. So there are two separate points on a graph. And then let's go draw out this graph right now. Just an example graph for our derivative. So let's draw some random curve. Doesn't matter what our graph looks like. And let's say that this right here was x1. So this right here is x1. Let's just call it point 1, p1, for the 1 value. So this is p1 and this is p2. Now, the slope between these 2 points, y2 minus y1 over x2 minus x1, is represented by a straight line. There's a straight line between these 2 points, and you can calculate the slope between these 2 points using your slope formula. But what is a derivative? Well, let's draw this slope out longer, actually. I think it looked like, did it look like this? Yes. We'll draw out longer, and let's say that this line goes out to infinity in both directions. So what is a derivative? Well, what happens if you bring these 2 points closer and closer? Let's say they're about this close right now. Alright, this is our new P1 and P2. And what if we brought them even closer to the point where they are basically in the same spot, like this, the orange line? Well, if you bring the 2 points super and super and super close, and you measure the slope of those 2 points, you get the derivative. The derivative is the slope of the 2 points between the 2 points that are extremely close to each other. Infinitesimally close, actually, to where they reside at the same point. So this kind of gets into limits, correct? You can represent the derivative like a limit, but I'll have a different video for the limit definition of a derivative. And I'm also going to be posting a Manum animation video for derivatives, because I think that would help out visualization better. If you guys know who 3 Blue 1 Brown is, I'm learning how to use the software right now, and it's absolutely amazing. But let's get back right into the video. So the derivative is the slope between the 2 points that are infinitesimally close on a graph. Now, what is this called? What is this line between these 2 points called? Well, it's called the tangent line. And this tangent line sort of only interacts with, locally at least, only interacts with 1 point on the graph. So this tangent line is right here, where it only intersects the graph at 1 point locally. Now, the reason why I say locally is because although some tangent lines, a tangent line could look like this, for example, right? But it'll still intersect the graph at like up here or maybe a little down here. But the whole point of this tangent line is that it intersects the graph only at 1 point within your small region. But let me add some slight nuance to the tangent line. So the slope of your tangent line is the derivative, correct? That's what we've been saying this entire time. But what if you had a straight line, for example? How do you find the derivative of the straight line? Well, since your tangent line should be, well, the point that is infinitesimally close. Let's drag 2 points that are super, super close to each other, and then measure their slope. Well, since this line is linear already, the tangent line is just the line itself. So your derivative of a straight line is just the slope of your line. But the point of derivatives is to measure curved surfaces, curved lines. So genuinely, the tangent line does not matter for your linear lines, the derivative is just equal to the slope of the line itself. So let's say this again. The derivative is the slope between two points, on your graph that are infinitesimally close. So these 2 points are dragged closer and closer and closer, and then you measure the slope of this orange line. It's a little hard to wrap your head around at the beginning, but just try your best to think of 2 points that are getting closer and closer and closer with a line that is marked off by those 2 points. I think I can, you know what, let me try to make this on Desmos right now, actually. So I got the Desmos working, and I just wanted to show you what I meant in a more visualized sense rather than seeing pictures. So let's say you have 2 points on a graph, and you can measure the average slope between those 2 points by subtracting their by calculating the change in y over the change in x. There you go. And what I said was that we brought these 2 points super close until we basically had them in the exact same spot. And this right here is what we call a tangent line. Now the tangent line intersects the graph locally at one point. Do you see how this line intersects the graph here? Well, that doesn't matter. All right, just that's why I said locally. It only intersects the graph locally at one point on a curve. So the slope of this tangent line is your derivative. You can actually represent this as a function. So let me show you what I mean by how to interpret derivative. Well, since the slope of the tangent line here is positive, we have a positive derivative. And since the slope of the tangent line here is, it's kind of 0, we're kind of in between 0 right now, this is what we call 0, right? The derivative here is 0, which isn't exactly 0 since there's still a slant in the tangent line, but we'll approximate to be 0. And then now the derivative is negative since the slope of this tangent line is also negative. And then let's go the other direction. Now it's negative again. Now it's back to kind of 0. And then now your derivative is positive. And then back to 0 here. So you can actually solve for these derivatives. They're not arbitrarily just going to be, oh, you're supposed to know what the tangent line looks like. You can make a function that represents the slope of your tangent line. And that is the derivative. You can calculate the derivative function using certain rules, which I will show you in future videos. But let's get back to the black screen. So let me add a few last things about derivatives. I'll show you the notation for derivative and just the names of all the notations. It doesn't matter really. So the notation for derivative is d over dx of your function. So this could be a representation of your derivative, and this is equal to your function, d of your function over dx. Or you could represent so this is how you can represent your derivative function. You can also represent f of x by y, since f of x is just your function for y. So dy over dx is your derivative notation. You can also, or your function of your derivative. So you can set this equal to your function of your derivative. Func derivative. Another way to represent a derivative is y f prime. And each prime represents an order of a derivative. So you can actually calculate multiple derivatives. You can have the first order derivative, the second order derivative. It doesn't matter. Second order derivatives will have 2 prime symbols. First order will have 1. That's all you really need to know. I think this is called Newtonian notation. This is called Leibniz notation. And you can also represent your derivative with y prime. Same thing as this. Since your function is of a function for y, you can just write down y prime as your derivative as well. All these are proper notations for your functions of your derivative. And on a final note, derivatives can be represented by limits. Notice how we dragged 2 dots close to each other. That sort of looks like a limit, correct? So you can solve for derivatives using there's a limit definition of a derivative, which will be my next video that I'm posting in a couple minutes. Your derivatives can be solved using a couple rules too, rather than using limits. You can use power rule, quotient rule. There's many rules that you can use, and there's many the trigonometric derivatives are a little different, but there's many rules you can use to solve for derivatives. And trust me, it's not that bad. But as always, if you have any questions, put it in the comment section. And if you found my video helpful, consider subscribing and liking the video. Thanks for watching.